Hello everyone and welcome to Applied Engineering channel. So in this video what we are going to do, we are going to discuss a three-stage economizer cycle simulation. So what this video includes, in the first part of this video we will see briefly what is three-stage economizer cycle, how it works, what are its applications and benefits, and then we will dive into cycle DHX simulation software, which is a semi-theoretical software, and we will simulate three-stage economizer cycle using R290, that is propane, and then R1234yf, two different refrigerants, and then we will compare their results. So stay tuned and see this video till end because you are going to get a lot of amazing ideas, results from it. So let's dive into this presentation and see what is three-stage economizer cycle and how it works. So first we will briefly explain what is a three-stage economizer is and how does this cycle works. So a three-stage economizer cycle is an advanced version of a vapor compression cycle that uses three stages at different intermediate pressures. It is usually paired with multi-port screw compressors or large centrifugal compressors. So how it works? So the liquid refrigerant from the condenser is expanded step by step through three expansion valves, as you can see here. So at each stage a portion of the vapor is separated and injected into the compressor at the matching intermediate pressure port, as you can see at this point and at this point, and the remaining liquid is further subcooled before it reaches the final expansion valve and into the evaporator. So this process increasing the refrigeration effect while reducing the compressor work and discharge temperature. So just think of it as a multi-level cooling plus vapor injection that keeps the compressor efficient and cool while boosting the system overall capacity. So what are the main applications where this cycle is utilized? So it is utilized in large commercial chillers, especially screw compressor chillers in district cooling. Number two, it is utilized in industrial low temperature refrigeration, cold storage, food freezing and ice production. Number three, it is utilized in high lift heat pumps where very large temperature differences must be handled efficiently. And number four, it is utilized in liquefaction plants for gases like LNG where staged cooling is critical. So what are the key benefits of this cycle? So number one is it has a higher COP and efficiency. It creates more subcooling, more capacity per unit power. It has lower discharge temperatures which protects the compressor and lubricating oil. The stable operation under high pressure ratios allows a single system to handle very wide temperature lifts. So a three-stage economizer cycle is not common in small units but in large chillers, heat pumps and industrial refrigeration plants, and it delivers big energy savings and improved reliability by combining deep liquid subcooling with multi-stage vapor injection. So now we will move on to our simulation platform, that is cycle DHX, and we will simulate the three-stage economizer cycle and we'll get some real results out of it. So let's dive into our simulation software. So this is our simulation software, that is cycle DHX version 2.0. What you have to do, you have to open it and you have to go to the file menu and then you have to go to open, and we are going to open the already example file. So you have to go to the examples and here you can see there are two examples given with the name of refrigeration two-stage economizer R290 and refrigeration two-stage economizer R290 simulate mode. So first we will open the impose mode and we will open this file. So opening this file will load all the data in this file. So as it name is two-stage economizer, when you will see it has refrigerant selected as a propane. In the cycle you can see it has selected this three-stage economizer. So you can use this example or these input values for the two-stage economizer as well as for the three-stage economizer. So what we see in this cycle, this is a three-stage economizer and there are two options. So the first option is regarding the intermediate pressure for high pressure stage or intermediate pressure for the low pressure stage. So whether you have to define the intermediate pressures by yourself or you have to select this option, that is optimize intermediate pressure. So in this example, this option is already selected, so it will optimize the intermediate pressures by itself. And in the cycle specification you can see it has already selected the impose mode, and the exchanger representation is by temperature change, and it has checked the established reference parameters, where you can see it has uploaded all the data for the heat exchanger geometries. It has calculated the area, and on this window you can see it has heat exchanger parameters and reference parameters which it will evaluate on this impose run, and which will be utilized for our simulation cycles. And here you can see in the compressor it has the isentropic efficiencies, and for the first stage or low stage compressor as well as for the high pressure compressor. And you can see that the efficiency values are similar, like isentropic efficiency, volumetric efficiency or electric motor efficiencies are similar. But here you can see one option, that is assign second stage isentropic efficiency independently of first stage. So if you want to change the efficiency of both compressors and you don't want them to be similar, you can just click it and then you can just change the isentropic efficiency of the second compressor. But if you want them to be same as in this example, so we will just take it as it is, and we will have the same isentropic efficiency for both the compressors. And here you can see it has already selected the cooling capacity, and the vapor line, suction line pressure drops are assumed to be zero, and the auxiliary power is also assumed to be zero. So first what we do, we run this into the impose mode, and we will impose this geometry in this simulation model, and we'll calculate the reference parameter which will be utilized for our further simulation runs. So let's run this simulation in the impose mode. So here you can see the results have been evaluated in the impose run, and here what we can see, it's a three-stage economizer cycle, and it says that the electric motor waste heat is applied to the suction gas. Because we have selected the electric motor efficiency in this simulation, so here we can see that the electric motor waste heat is also applied to the suction gas, and it will change the temperatures within the compressor, which I will show you in the state points. So the capacity is there and the efficiencies of the compressors are there, and here we can see the heat exchanger state points and heat exchanger configuration, and the inlet and outlet points and number of circuits used. And here in the thermodynamic cycle we can see all the state points of this cycle, how the temperature, pressure, mass flow rates are varying. And further moving on, we get this compressor and system results, where it has calculated the compressor power and COP of cooling and heating values, and the compressor suction volume, volumetric flow rate values. And further you can see it has calculated the heat exchanger results. So this was in the impose mode run. So now what we will do, we will close it and we will change it to the simulate mode, so we will get more results about the heat exchanger, overall heat transfer coefficient values, pressure drop values. So now we will change it to the simulate mode and we will run our simulation once again. So here you can see it has simulated it, and now we will see all these results are being generated, the thermodynamic state points, compressor and system result, heat exchanger results are being evaluated in the simulate mode, which were not present in the impose mode. So now we have all this data, the COP values and everything calculated. So these are the results generated by the simulation. Now we will see in detail what these results explain to us. So first what we will do, we will see the system schematic. So after clicking it, you will get this system schematic, and what this system schematic shows, it shows the temperature levels, the pressure levels, the density, enthalpy and entropy levels at different state points of this cycle. So for example, these are the temperature, and we can see that at the inlet of the evaporator the temperature is -10, and at the outlet of the evaporator before superheating, its value is being changed to -13.4 due to pressure changes, and then at after superheating it has further increased to -8.4, and at this -8.4 it enters the compressor. And because in the compressor we have considered the electrical efficiency of the compressor to be 0.95, so it has dissipated some heat, and it has also increased the temperature of the refrigerant from -8.4 to -7.2. And then at the inlet of the compressor we can see, due to this flash tank or economizer, the intermediate temperature is being changed, and then at the outlet of after compression it has been again increased. So similarly for the second compressor, and then in the condenser there is subcooling, after which its temperature is reduced, and then we can see after the first expansion valve there is an intermediate stream of vapor which goes to the compressor, and the liquid stream, it goes further below to the lower pressure after expansion. So there are three like stages for expansion, because there are three expansion valves there, so that is why it is called a three-stage cycle or three-stage expansion cycle. And here we can see after the third expansion valve the temperature is again reached our desired temperature of -10.6. So this is how this cycle goes. And furthermore what we can see, its TS diagram and we can see its pH diagram. So these diagrams you can see, and here you can see, for example, in the TS diagram you can see that the temperature levels is being divided almost equally in every stage. And the important thing is that the pH diagram, the pressure levels are also divided equally, because in these stages the compressors have to take this load, so the load should be divided equally, otherwise one compressor will have more load where the other will have less load, and that is not like mechanically feasible or good thing for compressors. It should attain equal pressure levels for the cycle to work efficiently. So this thing we have to see in the TS diagram, that the temperature levels are equally divided, and for the pH diagram that the pressure levels are equally divided. And what we can see, we can also zoom these values if we want to see them in more detail, that how the temperature is varying in each stage. And can also zoom these diagrams to see in detail how the pressure levels are varying in these cycles. So these are very important things. So further on what we can do, another thing about this is that it also gives you the line sizing information. So for that you have to click here. So what it is telling, that you have to decide what is the outside diameter you want in your cycle. You will just select that outside diameter and you can see the vapor velocity in it. And similarly you have to select the length of discharge is 1, and similarly for the same diameter you can see what is the vapor velocity and the length of the liquid line, and the liquid velocity. So accordingly, whichever outside diameter you will select, you can see the vapor velocity in the suction line of compressor, in the discharge line of the compressor, and the liquid velocity in the liquid line after the expansion valve. So depending on your outside diameter, you can select the vapor velocities, and you can select which outside diameter is more feasible for you. So it depends on the vapor velocities. For example, the rule of thumb is for the liquid, the velocity should be 1 to 2 meter per second, and for the gases it can reach up to 10 to 15 meter per second. So on based on these rule of thumbs, we just select the outside diameters of our cycle. And also one important thing in these results are that the compressor power, also the COP of cooling, COP of heating. Along with that, you also notice that the total refrigerant mass flow rate is 4.3177 into 10 raised to power minus 2, that is 0.04 kg per second. It is very important because now after R290, that is propane, we will go for R1234yf, and we will compare that how by changing the refrigerant the results vary. So this mass flow rate is very important in that aspect, and other things are the COP of heating and COP of cooling, and the pressure drops or temperature drops within the heat exchanger or the condenser and evaporator are also very important. So now what we will do, we will change the refrigerant, and we will go for another refrigerant, that is R1234yf. So we will go to the refrigerant and we will find R1234yf. We will select it, we will go back to cycle specification, and we will simulate this with similar conditions so that we can compare different refrigerants. So now we can see the results of R1234yf, and now we will see what are the changes as compared to propane in R1234yf, and we will compare these two refrigerants. So here we can see the change in the COP values, and here we can see the change in the glide values of evaporator and condenser. So we can see a big glide of temperature in evaporator. And the other thing, as I told you about the mass flow rate of the refrigerant, so here we can see that the refrigerant mass flow rate through evaporator is 7.6 to 10 raised to power minus 2. That is, you can say, 2 times that of propane. So actually the natural refrigerants, they have better thermophysical properties, and they use less mass flow rate, less charging as compared to these other hydrofluoroolefins and HFC refrigerants. So here we can see that the mass flow rate is being increased. So now what we will do, we will go and see the schematic of this process, and here we can see how the temperature has been varied throughout the stages, and we can also see that the inlet temperature of the evaporator has been changed. And other thing, we can see the TS and pH diagram, and in the TS and pH diagram, what important thing is that you can see the temperature glide in the evaporator is very high. In the evaporator you can see a lot of pressure difference, and here you can see a lot of temperature difference in the TS diagram. And you can also zoom it if you want to see the in-depth analysis or the variance in the pressure drops in all these three stages. And here you can also zoom to see the temperature variance in all these three stages. So another thing you have to see, like, should operate above the atmospheric pressure, because on case of leakage, air should not go inside the system. It can damage the system. So you can see how close it is to the atmospheric pressure and how much temperature glide is there. But although you can see the stages or the pressure stages in all these three stages are equal, and similarly the temperature stages are also equal. So this is how you can compare different refrigerant using this example, and this is how you can see how this three-stage economizer work, and you can compare it with different refrigerants, and you can simulate it. What you can do else, you can play with it, like you can change the heat transfer fluid temperatures, you can increase the superheat or subcooling values, you can change the cooling capacity values, you can change the isentropic efficiency, volumetric efficiency, or electric motor efficiency values, and you can see how it will vary, and you can have some real result data. So this is all about this video. If you like this video, please like it, subscribe my channel. Thank you very much.